Microchannel heat sinks are extensively utilized for the thermal management of electronic devices, serving as an effective cooling technique. These heat sinks are typically constructed from copper, given its high thermal conductivity. The channels, which are several millimeters or smaller, are arranged in parallel at the top of the heat sink, facilitating the flow of refrigerant through them. This design enables the efficient dissipation of heat generated by electronic devices. High cooling performance can be achieved through phase change heat transfer, particularly when the refrigerant reaches its boiling point at the heated surface and generates bubbles. However, the bubbles within the channel acts as a resistance, impeding the flow from progressing downstream and causing inlet backflow. In examining this phenomenon within a single channel scheme, the refrigerant is introduced in a liquid state at the inlet, where bubbles are generated by thermal energy from the wall. The remaining area is pushed out towards the channel outlet by the inlet liquid inflow, forming a high-density wave front downstream of the bubble. As bubbles expand due to the supply of thermal energy, the high-density wave front is pushed downstream towards the outlet. Concurrently, the inflow rate of liquid at the inlet gradually decreases, leading to a reverse flow phenomenon. If all the liquid exits through the inlet, vapor flows in reverse, and the high-density wave front reaches the channel outlet and is discharged, where the flow resistance is resolved. Subsequently, the backflowed vapor flows into the inlet, and the liquid returns to its initial point. Downstream, the liquid film on the wall intermittently dries out, leading to a rapid reduction in heat transfer due to the low thermal conductivity of the vapor. Therefore, predicting the periodic flow oscillation caused by surge and reverse flow are essential for understanding the cooling performance of the heat sink. The theoretical analysis was conducted by dividing the flow in a single channel into 4 regions: a liquid slug, an expanded bubble, a high-density wave front, and an annular flow vapor area. Each region was characterized by the acting forces of pressure, wall friction, phase change force, and surface tension. As a boundary condition, the channel inlet and outlet pressures were assigned the steady-state experimental condition values, and the mass of the fluid exiting the outlet during the oscillation cycle under the constraint condition was set to be equal to the steady-state experimental fluid mass. The transient state analysis was performed by simplifying the channel into a one-dimensional model. Analytical simulations demonstrate that injecting a blue-colored liquid refrigerant at the inlet propels the downstream regions towards the outlet due to a net pressure gradient. Orange-colored bubbles expand by the supply of thermal energy, pushing the yellow-colored high-density wave front downstream. However, the high flow resistance of the yellow-colored high-density wave front causes liquid and vapor to flow back towards the inlet. This backflow persists until the high-density wave front is discharged at the channel outlet, overcoming the resistance. The vapor and liquid refrigerant that flow back to the inlet are then reintroduced, forming a period. The experiment compared the predicted values under 34 operating conditions, confirming that the oscillation period decreased as the mass velocity increased. This is due to the decrease in surge period as the fluid inflow rate increases. Additionally, when the heat flux increases, the oscillation period also decreases. This is attributed to the increased supply rate of thermal energy and the consequent acceleration of bubble expansion. Due to the limitations of this model, the predicted surge period was longer than the reverse flow period, which was inconsistent with the experimental results. In the experiment, the periods of surge and reverse flow were similar. The issue with the model arises when a single bubble near the inlet expands significantly into the inlet plenum. This expansion prolongs the surge period because the vapor needs to be reintroduced through the inlet to complete a cycle. The 28 experimental cases that satisfied mass conservation showed high-frequency prediction accuracy, while the 6 cases that did not satisfy this condition exhibited significant errors. In this study, only oscillation frequency predictions were conducted, Liquid film dryout and corresponding changes in heat transfer characteristics related to frequency will be investigated in a follow-up study.